The difference between physics and philosophy is physics solves problems and philosophy makes problems.
It's the easiest thing in the world to decide whether you're watching the movie forwards or backwards.
I think a bunch of people are going to come, we believe, but we will see.
Hi, Mark. How are you? Nice to see you.
How are you?
Something is terribly wrong here. There's some kind of very vivid, obvious, weird tension. Good to see you. Between the absence of a time direction in fundamental physics and the presence of a time
I managed
direction.
to fall down a flight of stairs yesterday.
The way I function as a teacher, that I'll do a much better job if I'm frequently interrupted with questions.
Rutgers is good to you?
That's all appetizers. The main event for us is a symmetry called symmetry under time reversal.
Probability has two faces, one facing the mind and one facing the world.
The acceleration is identical in these two films, whether the film is being run backwards or being run forwards. Any process which obeys F equals ma as depicted in a film being shown forwards is going to obey F equals ma as being depicted in a film shown backwards.
But I don't have any control over the past. Well, why is that?
There is no machine that can tell you whether you were at rest or in some constant state of motion with respect to absolute space.
But I have some control of the future.
This is a really, really profound problem. The business, you say to yourself, gee, I don't know, that if I dropped something while I was in motion, it wouldn't land right at my feet. I'd leave it behind as it was falling down. This is false, okay?
Statistical mechanics is like a gold mine for philosophy. We're going to talk about the philosophical problems that statistical mechanics.
The history of the positions of all of the elementary particles in the world is the complete physical history of the world.
So hello, everybody. I'm Barry Loewer. That's David Albert, and we're running this seminar. I think I'm going to tell you a little bit about the seminar, where we're going to go with the seminar, and also, well, let's begin this way. I know that about 7 people signed up as more or less official. Then there are a bunch of people sitting in, and a bunch of people on Zoom from all over the place. I mean, like from places in Europe and Seoul, Korea. God knows what time it is in these places and stuff like that. Okay, so so that's nice. So I think for the people who are taking the class, who here, raise your hand if you're actually taking it as a real class. Okay, so people who are actually taking the class, can I just ask you to just say who you are a bit and what your background is so everybody knows?
Yeah.
I know a little bit.
I guess we can go this way. Hi, I'm Charlie. I'm a first year at Rutgers in the philosophy department. My background is non-existent.
Non-existent?
Yeah.
Everybody has an existent background.
I studied applied mathematics as an undergrad. So.
Any background in physics at all?
Only up to physics 3. Only up to like GR stuff.
Yeah. Well, you don't need anything more.
I'm Nikki. I'm also a first-year philosophy PhD here at Rutgers, and I also took physics in high school, so yeah, also kind of flying blind.
Cool. So I, as you probably know, I sort of semi-retired last spring. So I wasn't around in the fall, so I haven't met the first-year students really, though I've seen you. Okay, but hello. Okay.
I'm Abhay. I'm a physics PhD student, 5th year. My philosophy background is negligible.
So some people here will know a lot of physics, and but not much philosophy, and some people know a lot of philosophy, but not much physics. That's great, because we can teach each other.
Hi, I'm Sidan. I'm also PhD in physics, 4th year, and I like philosophy, but didn't get a chance to read a lot, mostly because leaving my head.
Where are you from?
I'm Chinese Canadian.
Say.
Chinese Canadian.
Okay. Yes.
My name's Nishan. I'm first year PhD in physics, but I'm just auditing the course. And I took some philosophy class when I was a master's student in undergrad.
Cool. Okay. And you?
Dad, I'm a first year philosophy here at Rutgers. I haven't learned any physics since high school as well.
Okay, so I guess we'll all get to know each other over time. And then there are other people here, a couple of people, that's Mark Lang over there, that's Ted Sider. Some of you who are philosophy students know them. And I know his name is Stephen, but I can't remember the last name. Wilpert. And he is a physical chemist. Anybody else who's not? And you should say who you are. What?
I'm just an artist, but
As an artist, yeah.
yeah, I love science and philosophy, so I just understand just a little bit to be here.
So we know each other because we had a long conversation the other day. Okay, I guess that's everybody who's here. Okay, so here's how I wanted to begin the seminar. I was thinking how I got into what David is doing in his book, Time and Chance. So one of the things I'd like people to read, and if I haven't sent you it's on the class website. Everybody here should have access to the class website. If you don't, send me an email so I'll make sure that you can get access to it. So David's book, Time and Chance, is like a wonderful introduction to the basic ideas in statistical mechanics. And he's going to talk about, I guess, the first two chapters, this class, maybe the next class. When he was writing that book, I was living in Ithaca, and he was sending me chapters as he was writing, to correct the spelling. Is that what you sent him? No, I'd be the last person in the world anybody would send something to correct spelling. But anyway, I was reading it, and I had taken a course in statistical mechanics as an undergraduate, or a course that actually had statistical mechanics as part of it. And I learned what it was, and it actually got me. One of the reasons I got interested in philosophy, in fact, was that from that course and another course I was taking, actually a history course, people were talking about probability all the time, and I was asking, what is probability anyway? And I was told to go to the philosophy department, and in the philosophy department they said, well, we think about that here, but there's a lot of different views about what probability is, and they had some very good teachers there. They didn't tell me what probability is, and so I spent most of my career sort of thinking about that and some other things. And I think it's very interesting questions about probability. We'll talk about that in this class. So David was writing his book, sending me chapters, and I had more background in philosophy. And I was thinking, statistical mechanics is like a gold mine for philosophy. There are a lot of issues that philosophers think about, write about, have written about, which statistical mechanics has something to say about. Now, some of this has become, fairly widely known. I don't know how much all the people here know about it, but part of the reason you know about it is because of David's work. But, and other people too over the years, particularly connected to the nature of time and the direction of time. So philosophers are interested in questions like, why is it that causes always come before their effects, or generally do? And what is the nature of causation? We'll talk about that in this course too. And philosophers have been interested in, why is it that we can do something about the future a little bit, not that much. I mean, I can wave my hand, and so that, and if I'm in an elevator, I can press which floor to go to, but like I can't change the presidency by pushing a button or anything like that. But I have some control of the future. But I don't have any control over the past. Well, why is that? Well, philosophers might have said that's just because of what the past is and what the future is, but that's not much of an answer. You want to know what is it about the world that makes that the case, about the fundamental world. It looks like you're going to have to turn to physics or to something even more fundamental than physics. And because some philosophers think that metaphysics has to say something about the nature of time to give an answer to that. So we'll talk about those questions in this seminar. More generally, statistical mechanics began by answering the question of how a certain macroscopic science, thermodynamics, fits in with the fundamental physics, Newtonian mechanics at the time. And of course, this is a very general question that philosophers think about. How does the macroscopic fit in with the more fundamental? We call it the microscopic. And statistical mechanics shows how that works for thermodynamics. And if what we're going to develop in this course is right, it gives an account for everything. Everything in the everything contingent in the world. So we'll talk about that in this course as well. So statistical mechanics has something to say about a bunch of philosophical problems, but statistical mechanics itself has philosophical problems about it. So if you're a physicist doing statistical mechanics, you can ignore what probability means. You physicists over here, do you know what probability is?
That's a mathematical definition.
What?
That's a mathematical definition.
Say that again?
That's mathematical definition.
Mathematical definition.
Yeah, it's a mathematical function, of course, but that's not what probability is in the world, is it?
I think, like, when you ask the question, what is probability, how broad you want to, like, give a definition?
Say what you're saying louder so I can hear it.
Oh, I was just wondering, when the question is asked, what is probability, how broad of a definition you want to, like, give?
Well, I wasn't so much saying a definition, but just sort of a gesturing. What facts in the world makes it true that the probability of a certain event is such and such? In fact, what does probability apply to? I don't want to answer this question now. I just want to bring up that this is one of the things we're going to talk about in the course. So one question is, does probably apply to specific events dated events? Does it apply to types of events or to both of them? Obviously, probability has something to do with frequencies, things happening over and over and over again. But exactly what's the connection between probability and frequencies? It's not exactly the same thing, but there's some connection. Okay, so we're going to talk about that because statistical mechanics, in order to really understand its foundations, you have to understand what probability is. And let me just go a little bit further about talking about probability. Probability also seems to have something to do with what you should think about an event. So if you're told that the objective probability of the radium atom decaying in the next minute is 0.7, that tells you something about what your belief should be. You should have it's called a degree of belief of a certain sort that's bigger than a half, that the radium atom is going to decay in the next whatever amount of time.
I guess this is the very first philosophy seminar that I have ever attended, and so you use the term philosophical question. Can you give like a definition, or like what do you mean exactly? It's a philosophical question. Like asking why.
Well, that's a good question. You want me to give you a definition or give you a philosophical answer? Anyway, definitions are great when you want to clear up words, when you want to explain what words you're using. Someone else, and sometimes people think that giving definitions of certain concepts tell you something about the nature of what the concept refers to, and that's a view that that's out there in philosophy. But in general, philosophical questions are questions of the sort that, you know, you're thinking about something like, why is there something rather than nothing? Why is there something rather than nothing?
So it's more like why something is the way it is, or why.
There's a good joke about that, but I'm not going to tell it. So the philosophical, so it's the things that sort of itch you. You wonder, why is that the case? Well, with probability, you're wondering, what are people talking about? There was a history class in which they were talking about the probability of certain events, and it was a statistical mechanical class where they're talking about the probability of certain types of events. I was wondering, is they using the word probability the same or different? What in the world makes the claims that they're making right or wrong? Okay. And as I was just pointing out, probability has something to do with what's going on in your mind also. So probability is a very interesting concept in this regard, and we'll get into this in detail later. Probability has a mind aspect. There's a great book about probability written by a great philosopher, Ian Hacking, if you know the name, called The Emergence of Probability. And in it, he says that probability has two faces, one facing the mind and one facing the world. And that's because probability makes a connection between what's going on in the mind and what's going on in the world. It's an interesting kind of concept like that, because some facts about the world seem to be a guide to how much belief you should have to some events in the world. I'm saying how much belief, but that's very crude. I would do better later on. Okay, so my point there was we're going to talk about the philosophical problems that statistical mechanics, I think, says something about, like connected to the arrows of time, the direction of time, why we can influence the future but not the past. There are epistemological issues like why we can know so much more about the past and in so much more detail than we can about the future. So someone who's interested in epistemology should be interested in this. Is nature causation? And in fact, as the class proceeds, the very last, I think, 2 or 3 meetings, we'll see how we can use the notion of probability to come up with an account of various accounts of causation. And the very last meeting, someone who's just written a book about causation, a philosopher, some of you may know David Papineau, some of you may know who that is. He's actually going to be around, so he's going to come and run the last seminar, and I'll put online his book. I'm not sure it's been published yet, but he has a book about the nature of causation. His approach is a little bit different from the approach that I want to take and that I think David wants to take, but it's not that different. But the probabilities that he wants to make use of are the probabilities that we'll talk about here, the probabilities that come from statistical mechanics.
Can I interrupt with the question? Sorry for my ignorance, but I know only that.
Just don't say that. Otherwise, I'll have to begin every sentence that I say with that.
So, the definition of probability I know is the frequency of events which occur under the same circumstances. So you take the same circumstances, you do it many times. You do many.
Certainly has something to do with that, because you might spend a little bit of time thinking about what you mean by the same circumstances. It's not obvious what that means.
It's really hard to control, right? To make it the same circumstances.
Well,
we can say, let this be the main features of the circumstances, and let's try to make it.
Certainly something like that is in the neighborhood of what probability has to do with. Okay, but of course probability applies to very specific events that only occur once too. So we want to know how that's connected to the kind of notion you're talking about.
Not really define probability, right? Because the way you mathematically calculate probability is just repeat events under the same main circumstances, and you count how many times the event occurred under these circumstances, and this will give you the probability.
But some events, as far as we know, at least within our epoch, only occur once, right?
Yeah,
but they might have a probability.
That's why you can try to simulate the system. I'm not saying there's going to be.
Oh, so you're really meaning not just the frequency of the actual frequency, but you're talking about what would happen under same circumstances, right?
Yeah. So like, my understanding was from historians, so like anyone tells like, oh, like weather forecast people say the probability of snow tomorrow is this. What they mean is that under the same circumstances, this has happened this many times, out this many times.
Like I said, that's a good stab. It's something in that neighborhood. We're going to talk about that later on. But you'll have to get clearer about what you mean by same circumstance.
Yeah.
Not obvious what that means.
Right.
Whenever you use the word same, actually, you should, I mean, there's one thing. One philosophers know when you use the word same, you should. That's a thing. You have to think hard about what's going on. But yes, there's something there. So their frequency and probability are connected to each other in some way or other. So I was just making the point, because I want to stop talking in just a minute, that the two parts, the two things that will go on in this course. One is what statistical mechanics has to say about various issues in philosophy, about the direction of time, and about connecting the macroscopic with the microscopic, and about degrees of belief. In fact, I will venture the view that the probabilities that statistical mechanics at least can be understood, one way of understanding it, the probabilities will apply to everything in such a way that it'll give, those probabilities are in some way play a role like truth in some way. They are an objective guide to what your beliefs or what your degrees of belief should be. Okay, what I just said maybe sound very obscure, but that's one of the things we'll talk about later if it didn't make sense right now. Okay, so there's what statistical mechanics has to say about issues in epistemology and issues in metaphysics, like controlling why we can control the future but not the past, why we can know more about the past than about the future, why causation has a temporal direction, and why, and something about how the relation between the macroscopic and the microscopic, that's the metaphysical kind of issues, and also there's epistemological issues that I mentioned a minute ago. Then there are issues about, philosophical issues about the nature of, that come up in statistical mechanics, like what is the meaning of probability, and another issue, if one pushes a little bit further, is what are laws? What are laws of nature, anyway? So that's particularly something that I'm interested in, and other people here sitting here are interested in too. In fact, people I know sitting here have very different views about this, so maybe that'll come up later also. And so we'll talk a little bit about that, but that's not the main focus of the seminar. Okay, so this is a tentative syllabus, which you've all looked at and you've all seen it, and it begins with talking about the background in thermodynamics and statistical mechanics. And that's what David is going to talk about. So he's going to take over. And you want to sit in this chair, David?
Sure, yes,
Yeah, why
that's
don't you sit in
okay.
this chair? Then I can sit in your chair and fall asleep like you were doing.
Thank you, Barry. You can sit here too if you'd like.
I'll come closer in this chair.
Good. Let me just say one or two introductory things. More or less repeating what Barry said, maybe in a very slightly different language. The thought here is that, or one of the things that I think we want to make a case for here, is that something of peculiar interest about statistical mechanics is that if you approach it in the right way, or if you approach it in what looks to us to be the right way, it turns out to be the science which is, in a way, sketching out the architectural structure of the entire scientific project. That is, it's the science which tells you about how the science of nature as a whole, all of the special sciences, biology, meteorology that we were talking about, economics, sociology, so on and so forth, are related to the fundamental physical sciences. And if it indeed can do that, it has a special kind of interest, as I said, because what it's presenting you with is a kind of crude architectural sketch of the entire scientific project. That's one of the things which gives it a tremendous amount of foundational interest, in my opinion, and I think in Barry's opinion. And that's sort of like the way that's the spirit in which we'd like to try to approach it here. It'll emerge what I mean by that. I mean, let me say very crudely what I mean by that. There was, and a good way to get into this, a good way to see this kind of significance of statistical mechanics emerging is to think about the problem that a lot of the founders of statistical mechanics were struggling with in the 19th century when it was first developed. And that is that there seemed like a particular problem connected with how fundamental physics, at that time, Newtonian mechanics or Maxwellian electrodynamics or something like that, how fundamental physics is connected with what seems like, as it were, the lowest level of the special sciences, which is thermodynamics, okay? And the particular challenge which struck people there, and the particular challenge which motivated the development of a lot of statistical mechanics was a particular apparent tension between Newtonian mechanics or Maxwellian electrodynamics on the one hand and thermodynamics on the other hand around questions of the direction of time, okay? That there was a sense in which in the second law of thermodynamics you get a time-directed fundamental law, and that is prima facie puzzling because the fundamental dynamical laws of Newtonian mechanics or Maxwellian electrodynamics have no time direction in them at all. So there was a puzzle about how they could possibly underlie the laws of thermodynamics, how there was any hope at all of reducing the laws of thermodynamics in one sense or another to the laws of something like Newtonian mechanics or Maxwellian electrodynamics. And it was this particular challenge and this particular focus on how something like a recognizable thermodynamic direction of time could possibly emerge from the time-symmetric underlying microscopic physics that was the sort of impetus that developed this whole structure of thought about how the special sciences. What I mean by special sciences are, all the sciences that have some limited domain of application, as opposed to fundamental physics, which is supposed to have an unlimited domain of application. How those two are supposed to be related to one another. So that's what I'm going to begin by talking about. Let me just say a word about available resources. I'm going to begin, we're going to make a lot of departures from this, but I'm going to introduce these topics crudely in the way I do in this book I wrote a long time ago that Barry was referring to called Time and Chance. For everyone who's officially registered, a copy of a PDF of that book has already been posted, and we'll, like Barry was saying, send him your email if you're not officially registered, and he'll put you on the list so you can get access to that too. Luckily, the book has been around for so long that there are now a couple of very helpful also background resources.
My copy is yellow pages.
That you ought to know about, and these have also been posted. One of them is a book of helpful essays about time and chance. The name of that book is The Probability Map of the Universe. And there are a lot of good essays in there. To whatever extent the presentation I give you is slanted or opinionated or anything like that, you'll find lots of pushback against those opinions in the essays in this book. Also, I recently found out that there's a Dutch philosopher at Leiden named Victor Jaspers, or Gaspers. It's one of these Dutch last names that's hard to pronounce, who's done a series of videos just giving people background, people lacking either the physics or the philosophy, do very helpful videos on the various different chapters of time and chance. There's a URL for those videos, those YouTubes that's been posted. That's really helpful too. And I'll be mentioning other more specific resources as we go along. Okay. So let me start by setting up this tension that I talked about the way in which the sort of very notion of a direction of time is presented on the one hand in fundamental physics and on the other hand in thermodynamics. So let me start with the fundamental physics end, and let me, as Barry said, it's a great thing that we have a variety of very different backgrounds in the class. It sounds like there are a bunch of people who know a lot about physics, have had much less exposure to philosophy. Others who are philosophy graduate students have much less exposure to physics. So just to get everybody on the same page, also let me encourage people. I'm glad to see that people were already doing this. It's a fact about the way I function as a teacher that I'll do a much better job if I'm frequently interrupted with questions.
Can I say something about that? Because there's some people who are on Zoom, and we should figure out a way they can also interrupt.
They can unmute and just
interrupt.
and interrupt.
And scream, yeah.
Right.
Right.
And yell.
And you're
Right.
welcome to do that.
Right. And I very much encourage, it'll help me do it better. I start to feel lost.
Yeah, I agree with that
if
too.
nobody's interrupting.
But you got to be loud for me right now.
Okay. So let me start. It's customary. I mean, first of all, it's faithful to the historical situation, but it's also customary in these situations to start out using as an example, using as a model, something that's customary in these kinds of conversations, in these kinds of foundational conversations, is to take as one's model of a fundamental physical theory, Newtonian mechanics. Yeah. Good. As I was saying, the usual custom in courses whose focus is foundational is to take as a paradigm case of a fundamental physical theory, for the sake of these sorts of conversations, Newtonian mechanics. There are all kinds of, well, let me put it this way. That's because this tension between the absence of a time direction in fundamental physics and the presence of a time direction in something like thermodynamics comes up in a particularly vivid and sharp and easy to formulate way in the context of Newtonian mechanics. And moreover, in the context of more, okay, now it's making me dizzy.
Yeah, I'm so sorry. I hit the reset button.
That's fine. It looks like modern art.
You can turn them upside down.
In the context of more advanced fundamental physical theories, like Maxwellian electrodynamics or quantum mechanics or quantum field theory or quantum string theory or so on and so forth, the tension comes up in a strikingly similar way. And there's some reason to be optimistic that if you learn how to deal with this tension in the context of Newtonian mechanics, you'll have a good start on dealing with this tension in more advanced fundamental physical theories. Although, in the case of more advanced theories, there are some interesting changes that take place in this issue, and we'll talk about them. Yes?
Do you think it's because we're talking about single body physics versus many body physics, where some kind of emergence happens in between? Because the thermodynamics is describing many bodies.
I mean, it's certainly the case that that the fact that, of course, Newtonian mechanics isn't necessarily about single particles. You can deal with any number. You can deal, well, no. In principle, Newtonian mechanics applies to any number of particles. And the time reversal symmetry of Newtonian mechanics is there for any number of particles. So just increasing the number of particles is not going to solve the problem. But it is true that when we're dealing with thermodynamic systems, we're dealing with systems consisting of many elementary particles. And that's going to turn out to be very relevant to what we're talking about. But it should be clear that it's not going to solve the problem by itself. Yeah.
I had a question, but when you wrote something you wrote in the time reversal variance in general section of the first chapter,
Right.
That there would seem to be two things. You want from a description, a complete description of the physical situation of the world, and that it be genuinely instantaneous. And I was wondering, like, I was wondering, like, if laws, if you're making a claim that laws actually have to be always, like, sort of Markovian, like it can never have any memory effect, like.
I don't think there's a claim like that in that definition. We'll get to that in a few minutes. It is usually taken, all of the fundamental theories that people have seriously entertained up until now have had this Markovian property. So we will. There's an interesting exception to that Barry and I have been talking about lately. But with that sole exception, a picture of quantum mechanics that's recently that people have been talking about recently. But skipping that, yeah, it's the usual assumption about fundamental theories that they are Markovian.
Yeah, maybe you should explain what Markovian means, because
Right.
a lot of people won't
Well,
understand.
but let's back up a little bit, because there are a lot of people with not. Let me back up before we get to that. So look, let me start out just by introducing the sort of picture of the world that we get from Newtonian mechanics. Couple of very basic things to say about it. One, this is a theory of the motions of particles, of elementary point-like material particles. And the thought is that if you want to take Newtonian mechanics seriously as the fundamental physics of the world, what you're taking for granted in some principled sense is that the history of the positions of all of the elementary particles in the world is the complete physical history of the world, okay? That everything else about the physical history of the world, in one way or another, supervenes, as philosophers like to say. That is, as it were, intuitively can be read off of the history of positions of the particles, okay? All Newtonian mechanics aspires to tell you about is how the positions of particles change with time, okay? And the thought is that if you have that, there's some sense in which you have everything, okay? That all there is to the world on the fundamental level are these material particles, and all there is to say about the history of the world, all there is to say about where the tables and chairs are, and who got married to who, and who won which baseball game, and what the weather was on such and such a day, and so on and so forth, is accomplished by giving some exhaustive catalog of the positions of all the material particles in the world at all times. There was a question, yeah.
Is it important that you're saying Newtonian, not Lorentz, kind of?
Yeah. At the moment, I'm just talking Newtonian. We'll get to more recent fundamental theories later. Yeah. Indeed. For our purposes here, assume there's an absolute background space. All we're concerned about are the motions of these particles with respect to this absolute background space. Needless to say, a lot of that gets modified. As we go to more advanced, more recent versions of fundamental physical theories, what's interesting is that the nature of the tension between the sort of time symmetry of fundamental physics, which I haven't defined yet, and the time directedness of thermodynamics, the nature of that tension remains pretty much the same, even as we go to more advanced physical theories, which is one of the reasons why it's convenient and helpful and simple and makes things more accessible if we conduct this discussion in the context of Newtonian mechanics. Okay, so anyway, yeah.
So this tension of this fundamental physics aspects with thermal or statistical, I wonder if it comes from on what scale that you're defining or studying a problem.
We'll get there, but just a cautionary word. Number of particles or scale by itself clearly isn't going to do anything, okay? We've got this exact symmetry of the fundamental theory. This symmetry doesn't depend on how many particles there are, doesn't depend on the scale we're looking at. Something else must be going on.
Well, we haven't quite got to the symmetry yet.
We haven't. That's right.
Right.
So let me do that.
Can I chime in with one other thing? Because you were saying we could read off from the history of the positions of the particles. David didn't mean that you could read it off.
Right.
I mean, you might remember this very famous quote because it's repeated often. I'm not sure the story is true, but Laplace, Napoleon asked Laplace something about with determinism or physics or something like that. And Laplace said, well, if you knew where the positions of the particles were, the fundamental physics will tell you where the positions of the other particles are at any other time. And that could tell you everything else, like David was saying, like who married who and so on. But of course, it'd take a lot of work to read that off. You'd have to know how the macroscopic concepts you're using are connected with the
Not only that, there's a lot of particles you need to know the positions of.
Yeah, I know. A lot of particles you need to know the positions of, sure.
But we're getting ahead of ourselves. Let's go one step at a time. So first, what the theory is about, what the theory proposes to give an account of, are the changes in the positions of these particles with time, okay? The way the theory works is that the theory says the way the particles move around is subject to a single, breathtakingly simple constraint, okay? That constraint is this.
David, could I ask you, this is going to be a little silly, but could I ask you to swing your arms above your head? That way I can on the board.
Yeah.
Let's do that.
It's not doing anything.
You look like you're flying. Or trying to fly.
Don't be discouraged. Keep going.
Really? Okay.
Okay, well, looks like someone
No,
collaborate.
now it doesn't like it doesn't like motion. Turns away from. It says to itself, "That guy's making an idiot of himself. Let me turn in."
But look at the board now.
Well, I mean, I'm doing my best, but
Yeah. Don't.
You can just say it. Everybody
let's not
knows
worry
what's on the board. Just say
So look, there's this famous Newtonian law of motion, F equals ma. Okay. For every particle, okay, the only constraint that Newtonian mechanics imposes, every particle has a certain total force on it. We'll talk in a minute about where those forces come from, about how they arise. But every particle at every instant has a certain total force on it. Every particle has a certain mass, okay? That's an intrinsic feature of that particle. And the constraint is that the acceleration of every particle, in case people don't know what acceleration is, velocity is the rate of change of the position of the particle, and the acceleration of any particle is the rate of change of the rate of change of the position. That is the rate of change of the velocity, okay? At the time in question, for people who know calculus, it's the second derivative with respect to time of the position. Good. We'll talk in a minute about where the forces come from, or let me talk now about where the forces come from. That'll give us a way of putting all the laws on the table at the same time. It's going to be a fundamental stipulation of at least the version of Newtonian mechanics that I want to talk about here, that all the forces there are arise as forces between pairs of particles, okay? That is, all the forces there are cases of these particles either repelling or attracting one another, okay? The paradigmatic case of a force for Newton is gravitation, okay? Newton writes down a law that involves, if I have a certain pair of particles, the attractive gravitational force between them, which is directed along the line that connects them, is equal to the mass of the first particle times the mass of the second particle divided by the square of the distance between them multiplied by Newton's gravitational constant, g, okay? This is a case of a force law. We might also imagine, say, laws of electrostatic repulsion. Okay, we won't need to talk about more force laws than that at the moment. So it might also be the case that these particles have, or some of them are electrically charged, either with positive charge or negative charge, or without electric charge. And there can also be electrostatic forces of repulsion or attraction, like, charges of the same sign repel each other, charges of opposite signs attract one another. The law of electrostatic repulsion also has a similar mathematical form. That is, the electrostatic force between two particles will be the charge of the first particle times the charge of the second particle divided by the square of the distance between them, and once again directed either attractively or repulsively along the line connecting them. Everybody with me? So we have this law, the law of motion. We have some force laws, like the law of gravitation, the law of electrostatic interactions. Those two are the only constraints that exist on how these particles can move, okay? That is, the rule is that these particles are allowed to move around in whatever the hell way they like, so long as their motions are always in accord with this equation. That is, there's just a constraint on how much they're accelerating, okay? And with these force laws, okay? Given the intrinsic features of these particles, their masses, their charges, so on and so forth.
Get the cat onto the blackboard.
Yeah, we seem to be having trouble directing the camera. I'm sorry. But there's not much on the blackboard. It just says F equals MA.
It's a whiteboard anyway.
Good. So, astonishingly, since these constraints at first glance look very weak, okay, it happens to be the case that if you are given a list of the positions of all the particles in the world at any one time, and their velocities at that same time, and a list of their intrinsic properties, their masses and their electric charges, and so on and so forth, it turns out that there is only one way for them to move, okay, all the way out to t equals infinity, in such a way as to be in accord with this, okay? This turns out to be much, much more restrictive than it might naively look at first, okay? Indeed, the demand that these requirements be satisfied turns out to amount to a fully deterministic theory of the motions of these particles in the following sense, that given a list of what particles there are and their intrinsic properties like mass and charge, given their positions and velocities at any particular temporal instant, everything else about their history is uniquely determined by that information, okay? And once again, it's uniquely determined just by the requirement that F equals ma be satisfied at every instant, given the force laws. Everybody with
Sorry,
me?
I didn't interrupt.
Yeah.
Hi, it's Jacob Baroness. Hey.
Oh, hi, Jacob.
Nice to see you. Enjoying
Hey,
Rutgers.
Jacob.
I know this is a bit of a subtle special case, but what about things like Norton's dome? What about
Yeah.
Gia's?
Yeah. Well, we may or may not get to that. There are exotic circumstances in which what I just said needs to be complicated a little bit. Perhaps we'll get to that. I don't want to talk about it right now. Good. Everybody with me so far? Good. Newtonian mechanics has a number of what are referred to in the literature as symmetries or invariances, okay? Let me give you a few examples. Suppose I start out with a certain configuration of particles, a certain set of initial positions and velocities. So let's assume, for the sake of this discussion, that the world consists of some finite number of these elementary point particles, okay? Suppose I start out with a certain configuration of positions and velocities of these particles, okay? Then Newtonian mechanics will predict certain future positions and velocities of these particles for any future time, okay? Suppose instead of starting out with that configuration, I start out with the same configuration but move to the east by 5 feet, okay? The entire block is moved over as a block, okay? The velocities all stay as they were, and all the positions are shifted, 5 feet to the east, okay? Then the future positions of those particles are always going to be exactly, they're going to match exactly the future positions in the original case displaced by 5 feet, okay? So the fact that you've moved it over 5 feet doesn't end up making any difference to the future spatial relations of these particles to one another, okay? Newtonian mechanics is said, what I've just described is called in the literature, the way it's referred to in the literature is that we say Newtonian mechanics is invariant under spatial displacements, okay? And one of the implications of a symmetry like that, of an invariance like that, is that it ought to be clear that if I were to try to construct a device, okay, if Newtonian mechanics is the true fundamental theory of the world, and I were to try to construct a device such that when I turn it on, it swings a pointer to one position on a dial if the position of the center of the universe is such and such in absolute space, and it swings it to another position on that dial if the center of the universe is at a different location, it follows from the invariance of Newtonian mechanics under spatial displacements that the construction of a device like that is in principle a physical impossibility. Okay? Because that device would have to behave differently. That is, the relative positions of the particles that make up that device would have to behave differently if I started it out here or if I started it out there in the same configuration. Okay? That is, it's a principle of Newtonian mechanics that there couldn't be a physical system, including you, of course, who's capable of detecting where you're located in absolute Newtonian space, okay? Of course, the spatial relations of particles to one another can matter a great deal, okay? But if you move the whole thing over as a block, there's no, you're going to get the same evolution relative to those initial positions as you would have gotten in the original case relative to the original initial positions. So, for example, it follows that there's no, that the existence of any physical mechanism which is capable of reliably detecting its position in absolute space is ruled out by this theory. Everybody with me? There are other symmetries. There's symmetry of translations in time, okay? So here's a feature of Newtonian mechanics. Suppose I start out with a certain set of positions and velocities for all the particles. I start the particles out with those positions and velocities at 5 p.m. And then I use the theory to calculate what the position and velocity of everything is going to be at 6 p.m., okay? What I mean by saying that the theory is invariant under time translations is this, that if I were to start them out with those same positions and velocities, not at 5 p.m., but at 5:15 p.m., then in that second case, the positions and velocities they're going to have at 6:15 p.m. are exactly the ones that they would have had in the initial case at 6 p.m. Everybody with me? Similarly, it follows from this that there couldn't be a device, okay? It's physically impossible for there to be a device, if this theory is true, which when you switch it on tells you what time it is, okay? You might think that clocks tell you what time it is, right? But that's not what clocks do at all. Clocks tell you how much time has elapsed since you switched them on, or something like that. But they don't tell you what absolute time it is. And there couldn't be a machine that tells you what absolute time it is if Newtonian mechanics is true, okay? And whereby true, I mean the true and complete physical theory of the world. Good. And then there's a third symmetry. There are a couple of more symmetries. There are similar symmetries under rotation. And maybe there's another symmetry that's important to mention before I get to the main one. This is a symmetry that's a little less intuitive. This is a symmetry that certainly Aristotle didn't think the fundamental theory of the world has. This is something that was discovered and pointed to very explicitly by Galileo. Galileo noticed that, well, he didn't know about Newtonian mechanics at the time. Newtonian mechanics turns out to be, to have another important invariance under the transformations that are referred to as boosts in the physical literature. That is, suppose I start out the world with a certain set of positions and velocities. Okay, good. Then they're going to, my fingertips are representing the evolutions of the positions of the particles. Good. Suppose I take the same set of positions and velocities, but I add a certain constant, not to the positions, as we did in the case of spatial displacements, but to the velocities. Okay? I say that all the velocities are the original ones except supplemented by an overall velocity of 5 miles per hour towards the east. Everybody with me? Then the resulting motions, if the original motions looked like this, the resulting motions are going to look like this. Okay? That is, they're going to be exactly the original motions, except that to each velocity at every time, you add 5 miles an hour toward the east. Everybody with me? It follows from this, and Galileo is famous for thought experiments demonstrating this. You have two ships at sea, and you see that one of them is getting closer to another, and you're wondering which one is the one that's actually moving, and you discuss whether there are any experiments you can do on the ships to determine which one is moving, and so on and so forth. And Galileo understood that what this invariance under boosts meant was that just as there's no machine that can tell you where you are in space, and there's no machine that can tell you what the absolute time is, there is no machine that can tell you whether you are at rest or in some constant state of motion with respect to absolute space. Okay? There's no machine that can do that. I mean, it's worth, an intuitive reaction that people sometimes have if they've never been told this before is you say to yourself, gee, I don't know, if I drop something and I'm stationary, it lands right at my feet, okay? But I have the intuition that if I dropped something while I was in motion, it wouldn't land right at my feet. I'd leave it behind as it was falling down. This is false, okay? This is not what happens. I think I can demonstrate it, okay? Here, I'm going to drop this while I'm moving. If I drop it while I'm moving, I give it relative to you a forward velocity. It keeps up with me and lands right at my feet, okay? And Galileo had tons of beautiful thought experiments like this, and so on and so forth. So that's another invariance of Newtonian mechanics. And it has, again, this kind of epistemic consequence. Because Newtonian mechanics is invariant under spatial translations, there's no machine I can build that tells me where I am. Because Newtonian mechanics is invariant under temporal displacements, there's no machine I can build that tells me what time it is. Because Newtonian mechanics is invariant under boosts, there's no machine that can tell me what my velocity is with respect to absolute space, even though, according to Newtonian mechanics, according to the sort of standard version of Newtonian mechanics that we're dealing with here, there are facts about all of those things. Good. Everybody with me so far? Yeah.
You say there are facts about all those things.
Yeah.
We're sort of imagining is that outside of space and time, God has his watch. And God.
I don't know why you're saying outside of space and time. Inside of space and time, there are facts about all these things. There are facts about where you are, facts about what time it is.
Well, you talk about the center of the universe. The universe is infinite. It's not going to have a center.
I don't imagine that there are facts, or at the very least, facts about whether you're moving with respect to space or not.
Yeah, I agree with that. But I was saying that a convenient way to think about this way is that outside, there is a kind of God's eye view.
Right.
That comes along with talking about Newtonian mechanics.
Yes, that's fair enough.
And if you're sitting outside of the universe, you can imagine God has a clock relative to his clock. There's a time.
Right.
That things are happening.
And there are locations.
And a location. But you can't.
And there's motion.
But you're inside the universe.
Right. And there's motion, and you can't ascertain any of that, okay? It's a theorem of Newtonian mechanics that you can't ascertain any of that. Okay, that's all appetizers, as Sidney Morgenbesser used to say. The main event for us is a symmetry called symmetry under time reversal, or invariance under time reversal. Here's the idea. Suppose that I'm shown a film of a certain physical process, okay? And I'm asked to guess, based on the laws of Newtonian mechanics, whether the film is being shown to me forwards or in reverse, okay? Newtonian mechanics has something called, has a symmetry called time reversal invariance. the essential content of which is, if Newtonian mechanics is true, there is no way to determine, based on the laws of Newtonian mechanics, whether the film is being shown to me forwards or in reverse. Let's just take a simple example. Imagine I'm shown a film such that in the first frame, so here's the surface of the Earth. Here,
Maybe because before you start drawing, maybe I have an idea of how we can make it.
oh, you do? Okay.
Okay, so.
So you want me to wave again?
Don't wait.
No, don't wave.
Mark, I think you're being tracked, Mark. Can I ask you to walk to the front of the classroom and be comfortable with that? I'm not kidding. I think the camera's focused on you.
That's because you're.
What can I say? It's, you got it or you don't.
Yeah, yeah.
I mean,
You're
you want me
stuck.
to
Yeah.
walk to the front?
It's tracking
Do you
you.
want me to embrace David?
What?
Pass along his charisma?
Look at that.
Okay, and I have stopped the auto track.
Okay, good, good.
No,
Thank you,
that's
Mark.
it.
That's it. That's it. Up, now it's off. Imagine you're shown a film that looks like the following, okay? In the opening frame, you see a material body stationary up in the air, a certain height above the surface of the Earth, okay? And as the film goes on, you see the thing accelerating more and more quickly towards the surface of the Earth, okay? And the film cuts off just before it hits the Earth, okay? Suppose you're shown this film in reverse, okay? What you're going to see is a body moving very quickly upwards, okay? And then moving more and more and more slowly upwards until it comes to rest just at that spot. Everybody with me? Okay? And here's what I'd like you to notice. Look at the force on this object is fixed. It's the Newtonian force of gravitation from the Earth, okay? So the force is constant. And what I'd like you to notice is that in every particular frame of this film, the velocity, of course, is opposite in every frame when the film is running backwards as when it's running forwards. But what I'd like you to notice is that frame by frame, the acceleration is identical in these two films, whether the film is being run backwards or being run forwards. That is, in each frame, you have a constant acceleration in the earthward direction, okay? In the original way of running it, the constant acceleration is making the thing go faster and faster towards the Earth. In the film in reverse, the constant acceleration in the direction of the Earth is making the body go more and more slowly as it rises. Everybody with me? Okay? So the acceleration is the same frame by frame. Well, if the acceleration is the same frame by frame, of course the mass is the same frame by frame. That doesn't get altered if you're running it backwards or forwards. The force is the same frame by frame, okay? So if F equals ma is obeyed in this direction of running the movie, F equals ma will be obeyed in the opposite direction of running the movie. And this is not unique to this particular situation. This just follows from the fact that you take a movie of any process which is in accord with the Newtonian equations of motion. If you run it backwards, A is going to be the same, M is going to be the same, and F, which only depends on the relative positions of bodies, is going to be the same, okay? So all of these are going to be unaltered. So any process which obeys F equals ma as depicted in a film being shown forwards is going to obey F equals ma as being depicted in a film shown backwards. Everybody with me here? Okay? So you take a movie of any process which unfolds in accord with the Newtonian equations of motion, run the film backwards, you're going to see another process, a different process, but one that's equally in accord with the Newtonian laws of motion. Everybody with me here? Good. This is what we allude to when we speak of the Newtonian laws of motion as being invariant under time reversal. Okay. Here's a slightly more vivid way to put it. Forget about the movies. Suppose I'm told the position of all I'm told the intrinsic properties of all the particles in the world at some given time, their masses and charges and so on. I'm told the positions of all the particles in the world at that time. And I am told how, so I'm given information about some particular time, and I want to calculate the situation of the world at some other time using the laws of Newtonian mechanics. I'm given the positions at A, and I want to calculate the positions at B, okay? And suppose that what I'm given is the positions at A and the rate at which those positions are changing as time scrolls towards B, okay? I'm not told if B is in the past, in the future of A or in the past of A, okay? All I'm given is the rate at which the positions are changing as time scrolls from A in the direction of B. Everybody with me? From Newtonian mechanics, I can obtain from that information all the positions at B without ever being told, and indeed without ever learning in the course of the calculation, whether B is in the future of A or in the past of A. Okay? The instructions for doing the calculations are identical, whether B is in the past of A or in the future of A. Everybody with me here? These are the senses. There's all kinds of interesting questions about whether the two senses of time reversal invariance I gave you are in fact logically identical to one another. They're not quite logically identical to one another. There's some discussion of this in chapter 1 of Time and Chance. I won't drag you through it right now. For most cases, these two criteria, the criteria of showing a film backwards and forwards and being unable to tell, and the criterion of the instructions for calculation being the same whether B is in the future of A or in the past of A. For most physically interesting cases, those do turn out to be identical. You can make up cases where they don't turn out to be identical. If people read through that and have some questions about it, I'm happy to discuss it. I won't go into it much now. At this point, I just want to present the basic intuition. What one means by saying that Newtonian mechanics is invariant under time reversal, or one way to put what one means by saying that Newtonian mechanics is invariant under time reversal, is that the laws of Newtonian mechanics will be of no help whatsoever, okay, in aiding you, in helping you to guess whether the film of a physical process that you're being shown is being run forwards or backwards. Yeah.
Two things. One is we're going to have a break at some point for a while. And can I summarize, what you just said is that Newtonian mechanics, you have no help in telling you whether you're coming or going. Which is often what my mother said.
So this was all for the sake of a pun.
And the same.
Yeah, I know lots of jokes. I won't tell them. Yes.
I was wondering why you said that it's not logical, like there's no logical connection.
So there are several ways. Let's see. There are several ways. I don't want to spend too much time on this, but there are several ways in which the instructions for calculating forwards and the instructions for calculating backwards could fail to be the same, okay? Here's one way. The fundamental law of nature is, I think this is an example I have in the book. The fundamental law of nature is as follows. There's a dot somewhere. I think in the book I call it a blue dot, but here it's a green dot, okay? And the universal law of motion is all particles proceed radially towards this blue dot at a velocity which is proportional to their distance from the dot, okay? So as they get closer, they go slower and slower. They never quite get there, okay? Needless to say, this theory is not invariant under time reversal. If I watch a film going in reverse, they're going to be going away. And the instructions for calculating from the present toward the future are different from the instructions for calculating from the present towards the past, okay? Good. Here's another way the instructions could be different. The law is the following. Yeah.
We stop here. Like, why it would be different going it this way or that way?
Because I mean, obviously, if I'm watching a movie, I could tell if the movie's going forwards or backwards. Okay.
Well, a single particle is on, right? We just discussed the example of going up or down.
No. Wait. We're not talking about Newtonian mechanics here. We're talking about a different theory. Okay. Here is the new fundamental theory of the world. Okay. There is some fixed blue dot somewhere in space. And all particles just move toward that blue dot at a specified velocity, which is proportional to their distance from the dot.
Yeah.
Obviously, if you're shown a movie and the particles are getting farther away from the dot, the movie is being shown in reverse. Okay? And the instructions for calculating toward the future, which is move everything towards the dot, okay, are different from the instructions for calculating toward the past, which is move everything away from the dot.
Pretty sure if I take this potential, which could lead to this motion.
There's no potential here. No. You're trying to interpret this as a special case of Newtonian mechanics. That's not what it is. Okay? This is a completely different fundamental theory. This is not a theory with F equals ma in it. This is not a theory with forces in it or with potentials.
Why couldn't it be? I can come up with a force law, which
because then this is going to happen. Then it would be different if this dot were in other places. It's part of the fundamental laws that dot is there. Okay.
It's the condition that you already know the time direction for the movie to be shown is that they move towards the dot.
Correct. This is a very simple theory. Don't be trying to imagine Newtonian systems that would imitate certain features of this theory. That's not what's going on here. This is a new fundamental theory. Okay?
Could you please reformulate? Because so far my understanding is that it could be I can come up with an internal system which would result.
No, you couldn't. That system, I don't understand. What would this would be infinitely massive, say?
Any center of mass of any Newtonian system.
No, it's not going to be like that. That's not what particles do in cases like that. Indeed, they would accelerate as they get towards the center. They wouldn't decelerate.
Depending on kind of force.
But anyway, if the question of whether or not one could imagine a way to imitate parts of this in Newtonian mechanics is beside the point. The game I'm playing here is I'm introducing a completely new theory, okay? And I'm telling you what's going on in that theory. Yeah.
I'm failing to see why this is completely different from the Newtonian case, because in the case for an object to fall down, we know, like, you say the physics is like in both time directions the same.
Right.
But we leave in one time direction. Therefore, to us, it's like the same condition as if we already know.
No, that's not true. I didn't understand.
Towards the blue dot.
Wait. It's not true in the world where we live that particles in the vicinity of the surface of the Earth are always heading down. That's not the case. If I throw a baseball up in the air, it's heading up, but it's decelerating the higher it gets. It's going more and more slowly. It's absolutely not the case in our world that particles in the vicinity of the surface of the Earth are heading down. That's not true. That's not what particles tend to do.
Yeah, but that's because you have different initial conditions for these two scenarios.
That's correct.
Right.
That's correct. Here, under all possible initial conditions, which are just initial positions of the particles, they always head towards this thing.
I think what's maybe is not being made absolutely clear to them. So
Yeah.
just giving an example of a theory which has
Yeah.
a time
Yeah,
direction. built into it.
I've been, I don't know, I thought I had said that a couple of times. Yeah, this is a completely different theory. And no, this is not at all like our everyday experience of the world. Here, there are plenty of initial conditions where the particles are going up, and there are others where they're going down. Here, there are 0 initial conditions where they're not heading towards the blue dot. Okay? It's a completely different theory.
Just to make it try to understand if I understand it correctly. On the left, the theory is such that whatever are initial conditions, the particles are moving toward the
Correct.
side. This is a
Correct. Correct. Okay, good. That's one theory that fails to be time reversal symmetric because the instructions for calculating toward the past are different from the instructions for calculating toward the future. Here's another way theories could fail to be time reversal symmetric. The world, there are a bunch of fixed blue dots scattered throughout the world, okay? And here are the laws of motion for the particles, okay? The laws of motion are exactly the Newtonian laws with the following exception. Every night at the stroke of midnight, okay, every particle jumps to the nearest blue dot, okay, and then continues from there, in accord with Newtonian mechanics with the same velocity it had just before midnight struck. Okay? Everybody with me? It should be clear that this theory contains complete instructions for calculating toward the future, and the theory is completely deterministic going toward the future. Okay? But if we try to infer backwards, if we're given the positions and velocities of all the particles at some later time, and we try to infer backwards past the most recent stroke of midnight, we don't know where the particles were. Okay? So this is a theory which fails to be time reversal symmetric, not because the instructions for calculating into the future are different for the instructions for calculating into the past, but because there are instructions, indeed deterministic instructions, for calculating into the future, and there are no instructions for calculating into the past. Everybody with me? So there are several ways, there are several distinct ways in which theories can fail this criterion of the instructions for calculating into the future being different for or the same as the instructions for calculating into the past. Those lead to, there are interesting cases to consider there. Like I say, there's a discussion of them in chapter 1. I don't want to spend too much more time on it now. And I guess, let's see. Yeah, is this, we go until 3? Should we take a break now?
We probably should take a break, probably about 20-minute break or something.
20 minutes or let's take a 15-minute break. Let's reconvene at a quarter to 2. Yeah.
I just want to make sure I understand the setup for this case.
Yes.
You're thinking of like, do you know like how they jump to the nearest, or you don't have?
Here's the rule. Here's the rule. You start, the particles start off with given set of positions and velocities and intrinsic properties. They evolve forwards from there exactly in accord with Newtonian mechanics. But at the stroke of midnight, what they all do is jump to the nearest blue dot. Okay? There'll always be a blue dot that's nearest. I mean, if they're right in between, I don't know, you have a rule there. They jump to the one to the left or something like that. But there'll always be a nearest blue dot. They jump to wherever that is. And then they go on with the same velocities in accord with Newtonian mechanics. Yeah.
I guess there's like a sort of like a ball around each blue dot where
Yeah.
we can't really say if the velocity is like coming in this way or like
It's not a matter of the velocity. They jump to the blue dot that's nearest to them in space.
there's like sort of like a ball around, imaginary ball around this blue dot that
If
you
they're
can't really say where that particle was before.
exactly, that's exactly right. Yes. All we know about the location of the particle right before midnight is that it was closer to that dot than it was to any of the others. But it could have been anywhere. Could have been anywhere.
Can I interpret it as you don't have continual access to the event along the timeline? You cut off like slices of a time period that you don't know what happens?
No. As soon as midnight strikes, they are at a blue dot.
Collapse thing, instantaneous thing.
Well, it's discontinuous.
Okay, yeah.
It's discontinuous. Yeah.
These are really weird theories.
Yeah. This isn't the theory. We're just making up theories in order to illustrate these logical points about what follows from what, about whether the instructions for calculating forwards and backwards are the same, so on and so forth. That's why I said, this is part of what I meant by saying for physically interesting cases, the movie criterion is going to turn out to be equivalent to the calculating forwards and backwards criterion, but it's not strictly logically equivalent. We can come up with cases where they're different, okay?
There are more realistic theories also.
Right.
David, can I ask you a quick question?
Yeah.
I think what was critical in your example there with the blue dots is that it's a deterministic jump, right?
Yes.
You introduced a discontinuity, but you made it deterministic.
Yes, this theory going forwards is a fully deterministic theory. Going backwards, it's not only non-deterministic, it's not even probabilistic. You just don't know. If you go backwards.
I understand.
Right.
Yeah, I
Right.
understand, but my question is, if instead you had introduced the discontinuity by means of a probabilistic process, some Poisson jump,
Right.
how would that change?
That's a good question. I need to know exactly what the rule. I need to know exactly what the rule is. I'm sure there are lots of other varieties of things one could come up with here. Yeah.
The reason I ask the question is because, and I know you're not in the realm of quantum mechanics yet, but, in quantum mechanics,
Right.
you have that kind of.
Oh, yeah. No, in the GRW theory, just, a quick aside for people who happen to know what this is. In the GRW theory, there are probabilistic instructions for going forwards. There are no instructions, probabilistic, deterministic, or otherwise, for going backwards.
Yeah, that's what I meant by our realistic theories.
Right. But good. Let's take a break, and we'll come back a minute or so after a quarter of it.
Any history, if you take a kind of normal history, then if you consider the time reversal, it would be extremely improbable.
So let me think.
So is it
Yes, I guess that's right. Yes. So it's not that it's strict. That's right. No, that's right. It's not a strict contradiction.
Yeah.
To the extent that the chances are modeled by actual frequencies, you have an ensemble. There wouldn't. What you can't have is, as it were, an ensemble that's displaying both of those kinds of backwards and forwards transition probabilities at the same time. Right. I guess that doesn't logically preclude those being the probabilities.
Maybe there would be something weird about a theory like that where it would wax or depends on models. Why are we getting?
Yeah, we're getting echo here.
Shouldn't be any. I turned it on, but it shouldn't be any more.
Oh,
no?
it's you. I
Yeah,
told you
I
not
wanted to see
do
what would
that.
happen. We're not doing anything yet. Is it still echoing?
No. No. Okay. Let me see. He just stepped out for 1 sec. I'll give him a second. Good. All right. So here's the deal. Any questions about what I've set up to now? There's still an echo somewhere, isn't there?
Shouldn't be any. If there is, I'm going to shut this off.
No, maybe there's, I don't know, maybe I'm crazy. Or maybe I'm crazy in that particular way, as well as everything else. Yeah.
So with the previous two examples, you wanted to say that the time reversal symmetry can be broken in two ways, right?
Right.
It either can be broken so that the rules are different from going forward and backward, or there could be no rule at all going.
Exactly. Exactly right. Exactly right. Exactly right. Good. Here's the tension. Okay. You say if Newtonian mechanics is true, it shouldn't be possible to tell, okay, just based on what I know of the law-like behavior of the world, okay? It shouldn't be possible to tell whether I'm watching a movie forwards or backwards, okay? And of course, the immediate reaction is, but that's ridiculous, okay? Let's not talk about watching movies of billiard balls colliding in intergalactic space or something like that. You watch a movie of somebody walking down the street or of a flower growing or of a car exploding or something like that. It's the easiest thing in the world to determine by looking at the film, and not because you know what happened in this particular incident, but just because of your familiarity with the robust law-like regularities that the world obeys. It's the easiest thing in the world to decide, based on that sort of general knowledge of the world, whether you're watching the movie forwards or backwards, okay? So something is terribly wrong here, okay? There's some kind of very vivid, obvious, weird tension between what we take ourselves, or what we're imagining here, that we take ourselves to have good reasons to believe about the fundamental dynamical laws of the world, namely that they're Newton's laws, or more generally, that there's some set of laws which has this time reversal symmetry, okay? And I'm going to say a little more in a minute about the extent to which that claim generalizes to electrodynamics, to quantum mechanics, so on and so forth. We'll talk about that in a minute. But imagining for the moment that we take ourselves to have good reasons for believing that Newtonian mechanics are the fundamental laws of the world, or that some time reversal symmetric set of laws are the fundamental microscopic laws of the world, and in some sense, therefore, the complete laws of the world, okay? Because everything else supervenes on the motions of these microscopic objects, or on the evolutions of these microscopic objects that those laws are about. Something's wrong here, okay? Because there are obviously many cases where it's the easiest thing in the world to tell whether the film you're being shown is being shown forwards or backwards, and moreover, in which the way you tell that has nothing to do with your familiarity with the particular historical event being depicted. It just has to do with your very general knowledge about the robust and law-like regularities that govern the way the world behaves. Okay. So something's wrong here. Let's make that a little bit more precise. And like I said, the business of coming to grips with this particular problem, I mean, this is in part maybe a historical accident, but it's in part because this is a really profound problem too, okay? This is a really, really profound problem. The business of coming to grips with this problem is what finally, at the other end of it, allowed people to emerge with a picture of how the various sciences, of how the various special sciences fit together with fundamental physics. That goes on to become what Barry and I here are going to try to argue. It, gives you the general architectural plan for the whole scientific project. So this problem is interesting, not just in and of itself, because these questions of the direction of time have enormous intrinsic interest, but because it's the problem that forced people to struggle in what turned out to be a really profound and illuminating way with the whole question of how fundamental physics and the special sciences fit together. So that there's a lot at stake here. There's a lot in play here. Okay. Let me begin to set the problem up in slightly more precise terms. It's often convenient. So the puzzle is in the way that we've just spent an hour discussing. The fundamental physical laws fail to make a certain kind of distinction between past and future, or fail to make a certain kind of distinction between watching a film in one direction and watching a film in the other direction. And there are all kinds of senses in which this doesn't mesh at all with our everyday macroscopic experience of making our way around in the world, okay? And it's convenient to divide the senses in which our everyday experience of the world are time-directed, okay? So we say that our everyday experience of the world has a time-directedness, which doesn't seem to be reflected, and which therefore we can't see how it could arise out of the time reversal symmetry of what we take to be the universal fundamental laws. It's often convenient, it'll be convenient in this discussion, to sort of crudely carve up this general time-directedness of our everyday macroscopic experience of the world into three different categories, okay? The first category, the one that's been most studied by physics, most extensively studied by physics, is what you might call the category of sort of prosaic, ordinary, physical time-directedness, by which I mean it frequently happens that smoke from a cigarette disperses to fill a room. We never see it happen that the smoke spontaneously goes back into the cigarette, okay? It frequently happens that when we bring two bodies at different temperatures together, their temperature equilibrates, spontaneously equilibrates. It never happens that we see two bodies that are in thermal contact with one another that aren't being worked on somehow from the outside spontaneously differentiate their temperatures from one another. It often spontaneously happens that ice sitting on the floor of a warm room melts into a puddle. Okay, it doesn't spontaneously happen that a puddle sitting in the middle of a warm room suddenly becomes ice. Paper burns, it doesn't unburn. People look older as time goes by, they don't look younger. There are clearly an infinite number of phenomena of this kind. This is what I'll call the sort of prosaic, ordinary, physical time-directedness of our experience of the world. It's going to turn out, and this is another breathtaking achievement of 19th century physics, that there is a very simple way of summarizing this fantastic variety of different time-directednesses of ordinary physical systems by means of something called the second law of thermodynamics, which we'll be discussing in a minute. Yes?
Maybe this is like a very, maybe I'm just abandoning curiosity itself here when I ask this question. But what I'm saying, but I was gonna say, does it make sense to say that, oh, if something is possible, then it should happen? Like, because we're saying here, these laws are kind of reversible,
Oh, I see what you're saying.
like, is that
How shall I put it? Our impression is that when we see paper, that if we were presented with a scene in which paper was unburning rather than burning, I don't know what the word is, deburning, you know. You got these flames and they get smaller and smaller, and there's an intact, uncharred piece of paper at the end. Our impression is that, I mean, our intuitive impression, and I'm going to try to make this more precise in a few minutes, but our intuitive impression is, no, that's not something that could happen and just happens not to happen. That feels like a violation of something that has the force in our conceptual architecture, that has the force of a law, okay? Pieces of paper just don't do that. It's not that we're all aware that pieces of paper could do that, and they just don't, okay? The microscopic laws and the macroscopic laws seem to have a real conflict here, okay? There's a famous quote of Arthur Eddington's, which I never completely understood, and it seems like kind of an exaggeration, but Eddington is famous for saying somewhere, if you've got a theory that time goes sideways, great, let's pursue it. If you've got a theory that violates experimental evidence, well, experimentalists make mistakes sometimes. Maybe we got to go back and check again. But if you've got a theory that violates the laws of thermodynamics, forget about it, okay? There was a widespread feeling in the 19th century that even more than, say, Newton's laws, these are paradigmatic of what we mean by law-like regularities. Okay, so at least intuitively, this isn't a logical answer to your question, but intuitively, your question seems to have in the background the assumption that this stuff about paper never unburning, that's not like a law, okay? That's just something that we understand is possible, but we don't see happening. I don't want to endorse this or deny it, but there is a strong intuition around in physics. Hold on one second. That's not the right way to put it, okay? That indeed, these are the paradigmatic cases of what we take to be law-like behavior. We knew about these way before anybody had any speculations about Newton's laws or planetary orbits. And the way we explain the force of what we took to be fundamental laws are by saying it's like thermodynamics, okay? They didn't have the word at the time, but it's like, to violate this would be like paper unburning, okay? That can't happen, okay? This isn't, strictly speaking, an answer to your question, and we're gonna be having discussions that more directly address that question a little later on. I just wanted to flag that that's not the way people were thinking about it in the 19th century. Yeah.
Yeah, some of these examples don't seem quite comparable, like smoke dispersing from a cigarette. Okay. If you burn something, you're changing its energy level.
Mm-hmm.
In addition to entropy.
That's correct.
I mean, entropy is always increasing in all the examples
Right.
you gave.
That's right.
But energy not necessarily.
That's true. That's true. But these are all going to be cases, as you've just said, these are all, it's going to be implied by the second law of thermodynamics that paper can't unburn. Just as it's implied that smoke can't collect into a cigarette. You're right, there's more that's changing there than just the entropy, the overall entropy of the situation. But the overall entropy of the situation is changing, okay, and is increasing. Yes, it's going to be the case that this is covered by the second law of thermodynamics.
So we started using this word all of a sudden, but I think
No. And I used it because he used it. I haven't introduced it yet. I will introduce it. I will introduce it in a few minutes. Good. So, okay, that's category one. Yeah, sorry.
Another question regarding this. So before quantum mechanics was known, it was impossible for people to think of the same thing simultaneously exist at two different places. To what extent do you think, though, that we universally agree that entropy cannot decrease? It's how the universe is, or it's just due to our limitation of our capability of perceiving?
I mean, I'm not sure what to say to that. First of all, we haven't gotten to entropy yet, and I'll introduce it in a few minutes. I mean, well, there's a lot to say there. It's true that quantum mechanics has surprises, all kinds of surprises in it. I guess I would disagree with you that among those surprises is that a particle can be in two places at the same time. On certain ways of thinking about quantum mechanics, it can be in a superposition of being here and here. That's not quite the same thing as being in both places at the same time. If you look for it, you'll only find it in one place. But anyway, forget about that. If you're asking, could we be wrong? Of course, this is the nature of the scientific inquiry. Could we discover tomorrow that all of this is wrong? That there's another part of the universe where all the paper is unburning all the time, and so of course we could be. Okay, we make the best guesses we can at any particular point in the history of inquiry. Our experience so far seems to suggest that paper can't, that there's some sense of can't in which paper can't unburn, okay? But of course we can be wrong about everything. That's science, okay? Good. Anyway, I was delineating three separate categories of time-directedness in our everyday experience of the world. The first one is this one that I'm calling the time-directedness of prosaic, ordinary physical processes. This is the category of time-directedness of phenomena that's going to turn out to be covered by the second law of thermodynamics in a fairly straightforward way, which we're going to discuss in a few minutes. Second category, there is what you might call an epistemic, an asymmetry of epistemic access to the past and the future, okay? The kinds of things that we take ourselves to know about the past, or the kinds of things that we think we can know about the past, or the methods we have of coming into knowledge about the past are very, very different than the kinds of things we think we can know about the future, the ways we come into possession of knowledge about the future, so on and so forth, okay? This is a very obvious, very profound asymmetry. On the face of it, if you keep reminding yourself that all I mean when I say I know this about the past or I know this about the future is going to have to come down to some kind of claims about correlations between physical states of my brain now and various events that occur in the past or future, or inscriptions on pieces of paper now, or distributions of emulsion on photographic plates now, and various events that are going to occur in the past and the future. That is, forget about fancy words like memories. I can't have photographs or tape recordings of things that are going to occur in the future in the same way as I can have photographs or tape recordings of things that occurred in the past, okay? I can't have records or memories of things that occur in the future in the way that I can have of things that occur in the past. There is a temptation which needs to be immediately squelched if this conversation is going to go anywhere, to think, no, it's just a matter of meaning, okay? It's analytic that I can't have memories of the future. Memories are by definition about the past, okay? This is just a way of cutting oneself off from what the problem actually is. And that's why I was instead of using words like memory, I was talking about correlations between distributions of photographic emulsion and a certain visual scene in either the past or the future, or inscriptions on pieces of paper, or states of my brain, or something like that. These claims about asymmetries in the kind of epistemic access we have to the past and future are clearly, whatever else they are, claims about the way the physical world evolves, okay? If we show the movie of my life in reverse, we're going to see, me having memories now of all kinds of things that we saw, that we see later on in the film, okay? And so on and so forth. Very crudely, in order to make this more precise, we'll have to do a little work, but there is this kind of asymmetry of epistemic access, and I hope enough has been said already to make it clear that this too should be puzzling in light of the complete time reversal symmetry of the fundamental equations of motion. Yeah?
Could you tell me what definition of correlation you're using when you're saying correlation instead of memory? Like, how do you define correlation?
There's a very simple case, okay? I have a photograph, of course this is no longer true with AI and so on and so forth, but at least in the olden days it was the case, okay? If I have a photograph of a certain scene, okay, that scene existed temporally prior to the photograph of it, okay? That's very crudely what I have in mind by correlations. Or if I have an accurate description in writing of the life of Napoleon, okay? The life of Napoleon occurred before the inscription was produced, okay? In the case of the inscription, the correlation goes through the English language, or whatever language it's recorded in, okay? And we'll want to be much more precise about this later on in the discussion, but crudely speaking, it should be clear, okay, that when we speak of the temporal asymmetry of our epistemic axis, we're saying certain kinds of physical states, a photograph of XYZ, come later in time than certain other kinds of physical states, the state of which this photograph is a photograph, okay? The photograph comes later in time, or the memory comes later in time, or the description in English of exactly what transpired on such and such a day comes later in time than the day itself.
But we can all try to describe what future we're not going to be like any
yes.
fictional photo research.
Yeah. No. It's not that those are always wrong. It's just that the inscriptions about the past are much more frequently right, much more easily right. Let's put it a slightly different way. It's perfectly possible in principle, if the system isn't too complicated, for me to predict where the billiard balls on the table are going to be 5 minutes from now. Okay, I do a very complicated calculation involving the present positions and velocities of all the billiard balls, and I find out where the 8-ball was, where the 8-ball is going to be 5 minutes from now. Okay, if I want to know where the 8-ball was 5 minutes ago, it's very often the case that I can do that very easily. Okay, I don't have to be smart to do that. I don't have to invoke Newtonian mechanics to do that. I can often remember where the 8-ball was 5 minutes ago, or I can have a photograph of where the 8-ball was 5 minutes ago. Okay, so it's not that I can't know the future, okay, but it's just that the kind of epistemic access I have to the future differs in all kinds of radical ways, okay, from the kind of epistemic access I have to the past. And when the system gets more complicated, I'm wondering if my friend is going to like this movie, okay? Well, maybe I could predict whether he's going to like the movie or not using Newtonian mechanics, using the current state of his brain, the exact stimulus he's going to be exposed to in watching the movie. I might have to know where he's going to sit in the theater and so on and so forth. Whereas if he's already seen the movie, okay, and spoken to me about it, it's just trivial. Any idiot can do it, okay? It's a very different kind of business than gaining epistemic access to the future. Given that the fundamental laws which are supposed to describe everything are completely symmetric in this sense, where is the difference coming from? Okay, there's a tension there. Okay, so that's the second level I want to divide the time-directednesses of the world into.
In general, I understand it, but like I can provide some examples where it's easier to predict where how things going to be in future than. It
is, yes, it is. Here's an easy case. You know, let's. Yeah, sure. Here's an easy case. I've got a gas in a box at equilibrium. Okay, it's really easy to predict that if I don't mess with it, it's going to continue to be in equilibrium as time goes on. It's much harder to predict, 10 minutes ago. Okay, 10 minutes ago the gas might have been in equilibrium, but it might also have all been concentrated in the left corner. It might also have been concentrated in the right corner. So yes, there are plenty of situations in which it's easier to know more from certain levels of evidence about the future. Okay, and we're going to need to be much more precise, okay, about saying what these differences are. But that there are dramatic differences between the kind of epistemic access we have to the past and the kind of epistemic access we have to the future shouldn't be in doubt. Okay, we're going to need to precify it up a lot more in order to have a real physical problem whose solution we can begin to speculate about. But it's clear that there's this kind of asymmetry. Third level, okay, what you might call I'm sorry, did you have a question? No?
Yeah, I'd like to hear.
Okay. Third level, what you might call the asymmetry of intervention or causal asymmetries or something like that. It's a very, very deep conviction with which we make our way about in the world as agents, okay? That by acting now, we can affect the future in ways that we can't affect the past, okay? There are lots of ways of fleshing this out. One way that's going to be convenient, at least tentatively, is to say that the future seems to have a very different kind of counterfactual dependence on the present than the past does, okay? If I wave my arm around in a certain way now, it might get the camera to focus on me, although evidence so far is to the contrary. And it might be a signal to someone which very much alarms them and eventually precipitates a nuclear war. Somebody denies Trump the Nobel Prize, God knows what could happen. Okay? The thought is I can wave my arms around until I'm blue in the face now, and nothing about the past or nothing interesting about the past or nothing substantial about the past is going to depend on how I wave my arms around. Okay? Once again, given the information that the laws that we're taking to be fundamental and complete have no such asymmetry in them at all, there's a puzzle. This presents a puzzle. This presents a tension. Okay? Good. Maybe there are others. I suspect, maybe there are others. I suspect that others that people will come up with are going to be able to be fit into one or another of these categories. Yeah.
With that last one, it feels more intuitively purely philosophical than the others. Is there any kind of empirical correlate? So like the first one, you don't see unburning paper.
Yeah.
Second one, you don't see photographs of the future.
Right.
I mean, there is that of, so
Right.
it's getting a little philosophical.
Right.
The last one, is there anything like
I
that?
mean, I would think so. I mean,
You don't have people trying to effectively.
well, that's maybe that's the trouble. Okay, I don't know what to say. It is what I have for breakfast tomorrow is more correlated with what I now wish I have for breakfast tomorrow than my wishes about what I had for breakfast yesterday. Okay? Certainly there are occasions where I wish I had something different from, I have food poisoning or something like that. So I wish I had some.
This causes this, but.
There is, maybe those aren't analogous, and maybe nobody ever intends to have X for breakfast tomorrow in the same way as they intend to have X for breakfast yesterday, okay? So that this is hard to test, okay? You say to somebody, okay, I want to do a test. I want you to intend to have X for breakfast yesterday in exactly the way you intend to have X for breakfast tomorrow. Maybe that's a psychological impossibility because it's so well ingrained in us. But
But hang on, the simpler thing.
Yeah.
Is an instance of this third thing just that, does it essentially not even essentially involve intentions? It's just you never have.
Mm-hmm.
Oh,
striking
definitely.
of a match causing a
Right.
fire,
Yeah.
Right. That's right.
That's right.
Yeah. Yep. It's counterfactual. There's an asymmetry of counterfactual dependence.
Or asymmetry of causation.
Right.
Same.
Right. Which are related. Good. So we have these three very obvious, very ubiquitous categories of time asymmetry in our everyday experience of the world, which, there's no words that are equal to how deep these asymmetries are of our conceptions of what the world is like, okay? And prima facie, certainly, when put beside the complete temporal symmetry of what we take ourselves to have good reason to believe are the complete and fundamental laws of the world, we've got a puzzle about how these things fit together. Yeah.
I was thinking about how to phrase this question, but it just sounds like the whole problem is that time is not like space.
Say more?
Like the dimension of space, you have access to I guess, to minus x and plus x, but
You mean you have epistemic access?
yeah,
Yeah.
I guess, yes.
But that's not, I'm not sure I understand. Time is not like space on the fundamental level either. It isn't, that is, I wouldn't say that the similarity or dissimilarity of time to space is the essence of the tension that we're noticing here between the fundamental theory and and our everyday experience of the world. Time, I mean, maybe we'll get a chance to talk about this. The way Newtonian mechanics is usually presented, time and space are completely dissimilar from one another, okay? So it's not like the puzzle is they're very different in our everyday experience, but the same on the fundamental level. They're not the same on the fundamental level, but there is on the fundamental level an invariance of the theory under time reversal, a symmetry of the theory under time reversal, okay? And if the laws of the fundamental theory are supposed to contain, in some principled sense, everything about the robust law-like regularities of the world, okay, then there's a tension there. Then there's a puzzle there. I don't think the puzzle on the face of it, I mean, I think there's a lot to be said about the relationship between time and space. Maybe that's a tiny bit off topic in this course, but maybe we'll have a chance to say something about it. But in the standard presentation of Newtonian mechanics, there's all the difference in the world between time and space. So the way to set up the tension isn't to say, in our everyday experience, time is very different from space, but in the fundamental theory, it's not. It's different in the fundamental theory too.
So I guess the point I was trying to make was like, when we say we don't have the epistemic access to future as we have.
Right. No, that's true. The kind of epistemic access we have to the right and the left is very similar. Whereas the kind of epistemic access we have to the past and future is not. And this is a good way to put it, okay? And this is a useful way to put it. That is the way to talk yourself out of, right? Often when you begin a conversation like this, people say about the epistemic asymmetry, even more so about the causal asymmetry, what the hell is the problem? Of course, you can only remember the past. It's the past, okay? Or it's memory or something like that. It's sort of analytic to the notion of memory that you only remember the past. One way to get them to see the problem, okay, one way to get them to knock them out of this kind of smugness, okay, is to say, look, suppose that you suddenly discovered that you only had epistemic access to things to your right and not to things to your left. You would demand a physical explanation, okay? Something's going on there. What is there, a wall, blah, blah. What the hell is going on here? Similarly, if you discovered that you could wave your arms around until you're blue in the face, this produces many effects to your right. It produces no effects to your left. You would want to know what the hell is going on here, and there would be no doubt in your mind that the science that is responsible for explaining this situation is physics, okay? And in that respect, you should be thinking, of time as at least to that extent similar to space, okay? The fact that you've got a theory which is invariant under rotations, under right-left, exchanging right with left, should make it mysterious if you suddenly discover that you can only know about things to your right, okay? Or that you can only affect things to your right.
But the question was, if the fundamental theories are already not saying that time and space are alike,
yeah,
then why are we saying that we should have the same kind of epistemic access to left and right as we do to future events?
No, you mean the other way around. We should have the same. Anyway, here's why I'm saying it. Because they do share the following, time and space do share the following feature in Newtonian mechanics. Newtonian mechanics is invariant under rotations, okay? And it's also invariant under time reversal, okay? That's not to say that time and space have the same metaphysical status, but there are these two invariances, and it's the invariances in the theory when put beside the non-invariance of our epistemic access that gives you the mystery. That's why the asymmetry of your epistemic access to the past and future should be as puzzling, okay, as it would be if there was an asymmetry in your epistemic access to left and right. Okay, not because time and space are metaphysically the same, but because the theory does share time and space do share this symmetry.
Just like air universal.
Right. Exactly. Yes.
So on the third point about the symmetry of the intervention of causality asymmetry.
Yes.
So maybe the problem is that we're using time reversal asymmetrical word causality to cause something, right? Maybe the word we're using for this is incorrect. Like if I'm saying
the word we're using for what?
The word we're using to describe things is already time reversal asymmetric. Cause A causes B already implies that A happened before B.
Well, no, my reaction to that would be it's like what I said about memory, okay? People say, of course you can only remember the past. Memory is about the past, okay? What you want to say to such a person is, okay, you want to talk that way, fine, but you're missing the point here, okay? So don't use the word memory, use the word epistemic access, okay? Or don't use the word causation, use words about counterfactual dependence or something like that.
Use the word kind of connected, right, or interconnected.
No, but just somebody says, if my hand were here as opposed to here, God knows what kind of differences it would make toward the future, okay? God knows what that ramifies into 100 years from now. But you go 100 years back, somebody says, if my hand were here instead of here, the Second World War wouldn't have happened. You say, gee, that's not the way I evaluate counterfactuals, okay? That doesn't seem right to me. Whether your hand was here or here doesn't make a bit of difference to the Second World War. It might make a lot of difference to the Third World War, okay? If, especially if one of these locations where my hand could have been is a nuclear launch button, okay, or something like that. It might make a big difference to the future. Hold on a second. Whether my hand is here or here, it doesn't make a difference, we don't think, to the occurrence of the Second World War.
Yeah, it cannot cause the Second World War, but the Second World War could cause you in future.
Yeah. No. But wait.
So
you were the one who urged us to get rid of this word cause.
Yes, that's why.
So no. That's what I'm doing. I didn't use the word cause just now. I just talked about counterfactual dependence. Okay.
Okay, what do you call counterfactual dependence?
Say it again.
What do you call counterfactual dependence?
So I'm sorry. Maybe I should have introduced this. So often in physics, okay, often in everyday life, but also in physics, we say things like, if I had released this marker 2 seconds ago, it would be on the ground now. Okay? This is a curious kind of statement on the face of it. It's not a statement which is, or at least it doesn't look like it's a statement which is true or false of the world, because the premise of the statement is false, okay? I say, if I had released this 5 seconds ago, it would be on the ground now, okay? Good. There's a puzzle about how we understand claims like that, what we take claims like that to be about, okay? But in ordinary scientific discourse, we agree thousands of times a day that claims like that are true, okay? Or some claims like that are true, some claims like that are false, okay? When I say, A counterfactually depends on B, I mean something like where this thing is now counterfactually depends on whether or not I released it 5 seconds ago, okay? And we think, okay, that lots of statements like if I had released this 5 minutes ago, it would have been on the floor now are true, okay? But we don't think statements like statements like, if, why am I blanking? Somebody give me an obviously false counterfactual in the other direction.
If I let it go, you would have had a brown shirt on, or if you had let it go, it wouldn't have been in your hand.
Right, right.
5 minutes.
No. If I had if I had let it go, right, 5 seconds ago, 2 hours ago, I would have had such and such for lunch. Okay? We don't think that statement is true. Okay? So there's an asymmetry, whereas it may very well be true that something I do with my hand now affects what I have for lunch. That is, counterfactually determines what I have for.
Been affected by what you had on lunch, and the fact that you let it go right now could have been affected by the fact that you had.
Yes. The question is, why only in one direction? Why do these counterfactual dependencies only go in one direction? Okay. Yeah.
So, just to pick up on that.
Yeah.
How would you respond to someone who said, well, there are all sorts of counterfactual dependencies that run in the other direction?
Yeah.
I mean, maybe we don't pay a lot of attention to them in ordinary life sometimes, but, you know, if the Cubs had won the pennant, they would have to have traded for a slugger.
Sure.
The previous
Sure. Just as in the epistemic case, there are all kinds of situations like we discussed with the box of gas where it's easier to know about the future than about the past. So one is going to have to be much more precise about formulating these things. But at the moment, all I'm hoping is sort of intuitively obvious is that there's, broadly speaking, a very big asymmetry. Right. And given the complete time symmetry of the fundamental laws, there's a puzzle there. Okay? There's something that we want to understand better there. Okay?
Last question before we
Sure.
move on. So
Yeah.
about the second point of asymmetry of epistemic access.
Yes.
Maybe the problem is not with the nature, but with the sensor, with us who have only access to the past but not to the future.
So here's a claim. Here's a claim. Suppose we were to meet a race of extraterrestrials. Okay. I mean, this is just something to reflect on. Okay. Suppose we were to meet a race of extraterrestrials. It turns out they like to ingest very different kinds of chemicals than we enjoy ingesting. Okay, that's not so surprising. They have a very different physical structure, or certain kinds of actions on the surfaces of our bodies that cause us a lot of pain produce pleasure for them, or they don't care about it at all, or something. None of that would surprise us. I propose that if we met extraterrestrials whose epistemic relationship to the future was just, whose epistemic relationship to the past and future was the inverse of ours, we'd be very surprised. Okay? We'd be very surprised. Okay? Or we'd be very surprised to be able to build computers or robots whose epistemic access to the past and future is the mirror image of ours. Okay?
It's not very hard to measure, right? Like, there are many examples in fiction. Like, you can take, for example, the movie Arrival, where extraterrestrials have access to the future and past.
Yeah, that's. I mean, when you say it's not hard to imagine, I would dispute. So, Arrival is a fun movie. It's not imagined in very much detail exactly how the aliens did this. Okay, and I think we'd be flabbergasted. Okay, to run into aliens whose epistemic relationship to the past and future is the mirror image of ours. This particular kind of asymmetry in epistemic access, now this doesn't, what I'm about to say doesn't prove anything, but I believe it's true. It feels very deep, okay? It feels very deep. It feels exactly as deep as the claim that paper doesn't unburn and so on and so forth. It feels like there's a very robust, it's not as if we've encountered species of spiders, okay, whose epistemic access to the past and future is the inverse of ours, okay? It's not just a physiological matter, okay? If we came across some spiders whose epistemic access to the past and future was the mirror image of ours, we'd be fucking flabbergasted, okay?
It's a lack of evidence which makes it plausible that it's not the problem with us, it's just general feature of everything.
It feels like it's a very general feature. Somebody might say, like you were suggesting a few minutes ago, okay, so we never happen to have seen paper unburning. Bad luck for us, okay? Well, maybe. That's not the way it feels. That's not the way it feels. Yes?
Yeah, people use jargon to avoid using words that have baggage and other connotations that just don't want to deal with. What problems are there with using words like epistemic access instead of memory, or counterfactual dependence instead of cause?
I mean, as you said, it's just about avoiding the baggage. One way of not seeing, one way of sort of, defending oneself from the problem that I'm trying to put on the table is to say stuff like, of course you can't cause the past. Causes come before their effects. That's part of the meaning of the word cause, okay? Or of course you can't remember the future. Memories are by definition of the past, okay? You want to say to the person, you're completely missing the point, okay? You're just shielding yourself from the problem. This isn't a problem that's going to be solved by linguistic analysis, okay? This is a real problem for physics, okay? That's what one wants to put on the table here, and that's the worry about using these words with baggage. Right. Good. Good. Let me say a few more words about more modern and more contemporary physical theories. I wrote this, how long did I write this? I wrote this book, I guess, 25 years ago, or something like that. And in the rest of chapter 1, in the rest of chapter 1, I present a sort of, how shall I put it? I present a bunch of claims about what it means in general for a theory to be time reversal symmetric. A lot of people pushed back against this general definition of time reversal symmetry, and I'm now confused about. I think a lot of the ways people pushed back are probably right, and I just didn't think about it hard enough. I can console myself that I provided the service of putting the question very explicitly on the table in a way that it hadn't been put on the table before. But I think a lot of smart people pushed back on this in a lot of interesting ways, and I'm not sure what I think anymore about what the correct general notion of time reversal symmetry is. So I invite you to take a look at the latter parts of this chapter, but I want to make clear what the surviving and significant conclusion that comes out of this chapter is. So here's what everyone agrees is true, okay? Like I say, I talked about Maxwellian electrodynamics. On my strict definition of time reversal symmetry, Maxwellian electrodynamics turned out not to be time reversal symmetric. Lots of people, Jill North here, among other people, pushed back on that. in a way that I think is interesting, and in a way that I'm not at all sure I disagree with. There are subsequent debates about whether whether Schrodinger quantum mechanics is time reversal symmetric or not. I was saying it wasn't here, so on and so forth. Good. Happily, the upshot of all this is that there's a certain deep sense in which none of that matters, okay, in the following sense. What's uncontroversial is that every microscopic theory, well, there's one interesting exception to this in quantum mechanics, the GRW theory of the collapse, which we've been talking about, which we talked about a little half an hour or so ago. Put that aside, okay? With that single exception, which we can discuss later on in the course, every single proposal for a fundamental physical theory that anybody has taken seriously since the 17th century, okay, since Newton, has the following feature. It is what you might call time reversal symmetric insofar as the motions of material particles are concerned, okay? That is, it's true of every one of these theories that if, according to this theory, it's possible for a set of material particles to move around like this, okay, then it's possible, according to that theory, for the set of material particles to occupy exactly the reverse sequence of positions. The difficulties arise when you also include fields, okay? And if you demand that what you mean by time reversal symmetry is that the fields have exactly the reversed sequence of configurations and so on and so forth. That's where things get dicey, but it's a feature of every single fundamental theory that anybody has taken seriously, as I say, since the 17th century, with this single exception, which I'll talk about later. It's an important exception. But put that aside for the moment. With that exception, all of these theories share this feature of what I'm calling time reversal symmetry insofar as the motions of material particles are concerned, okay? And that's enough to set the tension that I've been putting on the table in motion, okay? If you know, almost all of the asymmetries we've talked about are time asymmetries in the behaviors of material bodies made of these particles. Smoke spreading out instead of collecting into a cigarette. Temperatures equilibrating, which is about the motions of material particles that make up these gases, so on and so forth. Yeah.
Are you, so the picture you got is with a field theory like in electrodynamics, the supervenience basis is just the particle position?
No, it's not that. But that's enough. If the particles, if the
It
laws...
would be weird. You have this weirdness measure. And if the particles were reversed, that's a sufficient condition for you having a scenario that's weird enough that we never see it. So
Correct. It's not that everything, the claim, that's right, the claim isn't necessarily that everything supervenes on the particles, but yes, if the particles were going backwards, weird shit would be going on, right? In violation of the thermodynamic asymmetry, in violation of the epistemic asymmetry, in violation of the causal asymmetry. Right. That's the idea. So the claim is, insofar as this problem of the direction of time is concerned, it's enough to have this symmetry, time reversal symmetry, insofar as the motions of particles are concerned, to set this tension up. Right. Yes?
Yeah. Mind wonders why it's saying that it's already kind of digested theory, but there is an embodied equation of motion with respect to what happens to quantum particles in distributed systems.
Say, yeah, No, but the dissipation is not a fundamental process, okay? There's no, for any dissipative process, there's an anti-dissipative process that's also a solution to the Newtonian equations of motion, or also a solution to possible motions of particles in Maxwellian electromagnetism or anything else. Yeah, what you're calling dissipation is exactly an example of what we've been referring to as the temporal asymmetry of macroscopic phenomena. Okay, why there shouldn't be anti-dissipative systems just as there are dissipative systems is one way of putting what I'm calling the thermodynamic level of this tension.
I'm not sure there is anti-dissipative Lindblad equation.
Say it again?
I'm not sure there is anti-dissipative Lindblad equation.
No, but this is, Lindblad equation is not a fundamental equation. It's an equation that describes dissipative phenomena, okay? But for anything that happens, okay, and any solution to the Lindblad equation, which is an approximate solution to the Newtonian equations of motion, then there'll be another solution in which everything is going backwards, in violation of the Lindblad equation, okay? We're taking it as our premise here, that the fundamental and complete theory is not described by a Lindblad equation. It's described by F equals ma, okay? Something like the Lindblad equation or any kind of dissipative equation is going to be useful in the way that the laws of thermodynamics are useful for describing all kinds of situations and so on and so forth. It's not our premise here is that whatever the fundamental theory is, okay, it has this time reversal symmetry insofar as the motions of particles are concerned. Yeah, well, I'm sorry. Yeah.
It could be that physics students are not so attuned as philosophers of physics students are to the difference between fundamental and non-fundamental.
Could be.
Laws, yeah.
Well, but did you want to say something about that, Bert? It sounds like you did.
Because that seems what was going on over here.
Right.
It's very important to distinguish the fundamental laws from the non-fundamental laws. And there's a conception of the universe that there are fundamental laws and there are non-fundamental laws. But it might be that when you learn physics, you don't really pay attention to that distinction. I'm not sure.
What do you mean by a fundamental physics?
Well, I mean, a couple of things. One could say, but here's one very simple thing. Its domain of applicability
is
everything. Okay? There are no exceptions to it.
But that would circle back to at the very beginning when I was talking about scale. You give an example of scale of like number of particles, but in physics, sometimes when we think if a theory is fundamentally enough or not, we mean that it would apply to all energy scales or like distance. So here you mean the domain of
Applicability, right.
So that would, I assume you mean that it applies to all situations, like to all scales.
Yeah.
That's what you mean by it.
Yeah.
Then I don't think Newtonian physics is fundamental.
Well, let's see. I mean, Newtonian physics isn't even true. That's a good reason why it's not fundamental. Like I said at the beginning, we're taking Newtonian physics as a sort of toy example of a putative fundamental theory. We don't know what the fundamental theory of the world is yet. Certainly, quantum mechanics is closer to being a fundamental theory than Newtonian mechanics is, but first quantized quantum mechanics is certainly not a fundamental theory. Neither is quantum field theory. We don't know what the fundamental theory of the world is yet. We do know the following, that every proposal for a fundamental theory, okay, that has been put on the table since the 17th century, okay, has had this feature of time reversal symmetry insofar as the motions of particles are concerned that I've been talking about. Of course, that could fail tomorrow. Okay. So far, though, I mean, if you wanted to put this dramatically, okay, you could put it this way. Not that I would want to put it dramatically. But if you wanted to put this dramatically, you might say, you know, there's this amazing story in physics since the 17th century. Every conviction has been toppled, okay? Determinism, the separateness of space and time, the dimensionality of the world, all these kinds of things have been overturned by various scientific revolutions, okay? Amazingly, the one that hasn't is what I'm calling time reversal symmetry. This has been shared by all of these theories, okay? So you might say the entire history of science is sort of modern physics. By modern, I mean since the 17th century, is screaming at you, okay? I don't know what's true, but this is, okay? Okay, I don't think I believe that, but one could tell the story that way. So of course I don't know what the right fundamental physical theory is. Okay, we don't know yet. We're using this as a model. Okay, we're using this as a sort of toy model. But of course, the reason we're paying attention to it is because we hope, okay, that whatever we learn from resolving this tension in the Newtonian case is going to be helpful in more up-to-date cases as well. Okay, we have to, yeah.
Go ahead, Spawn. Oh, okay. I know you're deferring discussion of quantum mechanics and GRW and all that.
Right.
You know, on this topic of, you know, if we come up with a new theory. So let's say we do come up with a new theory that explains everything much better than the theories we have, so we're inclined to adopt it.
Right.
And it has this asymmetric feature similar to GRW or whatever. You know, do we conclude then that sort of the fundamental, that sort of Tim's idea that there's an arrow of time actually built in?
No. I don't think we would conclude that. That's a good question, and lots of people do speak as if the theory that turns out to be true doesn't have this time reversal symmetry, that means there is a direction of time built into the fundamental metaphysical structure of the world. Just very briefly, because we're not letting everybody else in on the conversation here, but just very briefly, if you were to rewrite the GRW theory, not as these collapse contractions occur toward the future, but that all of them occur in the same temporal direction, that there's a correlation between them, I think you'd have for any purposes, any scientific purposes I can think of, exactly the same theory, but it doesn't depend on there being any fundamental metaphysical direction of time.
Isn't there a sense in which that's kind of indeterministic? Because you take a point, you take another point, tell you what's happening here. Tell me what's going to happen here. You say, oh, I have no idea.
Wait, what do you mean?
Because as far as the laws are telling you,
Yeah.
there's going to be a determination in one direction or the other.
Right.
But if you grab 2 points and you don't say at the fundamental, you don't have anything at the fundamental level to say, well, this is the future one.
Right.
The theory isn't going to tell you what's going to happen over here, given what's happening over here. It's going to say, at one or the
Wait,
other.
I don't know what you mean by happening. Let's think of GRW. I have a collapse over here. That is, I go in this time direction from spread.
So the stochastic theory, you say, here's what's happening here.
Yeah.
Here's another point quite close to it.
Right.
In time.
Right.
The theory is not going to give you a chance about what's happening at this other point. It's going to say, the theory is going to say, with respect to one point or another,
here's what the chances
two directions from the initial point, there is a chance with respect to one of them or the other there's a chance of a collapse. But if you fix an initial point and you fix a second point, the theory doesn't say anything about probabilistic or otherwise about what's going to happen at the second point. So the taking a theory, trying to make a theory in Tim's style, but then making it fundamentally asymmetric in time by saying it's a constraint in the whole global.
You mean fundamentally symmetric?
Sorry, fundamentally symmetric.
Yeah.
In a sense, introduces a kind of indeterminism, is what I'm saying.
I'm sure you're right, and I'm just being slow here. What can we do this specifically saying something like GRW?
I thought it was just doing that.
So I have at a certain place the following process. The wave function is spread out at a certain time. At another time, it's clumped. Okay. At another nearby time, it's clumped. I haven't said anything about a direction. Okay. Right. Now I say about this other nearby event, the sequence of unclumped to clumped is going to be in the same direction.
That, you can pick some things and the theory will have something to say about it.
Right.
But if you take an unclumped portion of and then you specify another time.
Yeah, I see.
What are the chances of this or that happening at that other time?
Right. It won't tell you. Right you are. You didn't mean indeterministic. Well, you meant not even right.
Sorry,
not even stochastic. Right. Yeah. Yes, I agree with that.
I don't know whether to be bothered by
that's right. No, I agree with that. It's not clear to me that one should be bothered by it. Right. Good.
David?
Yeah.
Hi, this is Marlon Reisinger. I have a much simpler question. Oftentimes in these discussions, the distinction is being made between macro and micro, or macro and fundamental. Is the distinction between macro and fundamental simply the same distinction as between fundamental and special science? Or
let's see.
If it's not, can you just comment on how one knows whether a description of a system is a macro description or a fundamental description?
So let's see. No, I would have thought the distinction, I'm not even sure if I kept your question straight in my head. I would have thought the distinction between fundamental and special is the useful distinction. That is, I don't know what, there are computer memories that are very microscopic in the way they function, but computer science is a special, it may be that I'm missing the point of your question.
Well, let me try one more time and then I'll drop it. Oftentimes the second law descriptions are said to be descriptions of macro.
That's true. In that case, it's true. Yes.
Yeah. So I just asked myself, how does one know whether a description of a system is a macro description or
let's see. So I may be missing the point again, and that doesn't mean you should drop it. But let's see. My answer off the top of my head would be a macro description is one that applies to a number of microscopically different descriptions, and not the other way around. Okay, that is part of what I mean by the relation I have in mind between macro and micro is that for any given macro state, there will be many microstates that realize that macro state. Okay, but for any microstate, there's only one macrostate that it realizes.
And does that distinction, as you just described it, correspond to the distinction between a fundamental description of the system
and a special science description?
Yeah, and a description in the special sciences.
So that's a good question. I'll be happy to take the bait. Suppose I say yes. Are you envisioning some kind of trouble that I get into?
No, I'm not ahead of you, I'm behind you.
I see. So I would, my first reaction would be to say yes, but but I'm prepared to believe that saying that would get me into trouble. And if that's the case, I'd be eager to hear about it.
I think
But you're right. But one thing that you were pointing out was that the idea of something that applies to everything, and the idea of being maximally fine grained are not the same ideas. I think that's what you were pointing out, right?
Dr. Loewer, you had a question about
the course load. Like, we enjoy the structure of the course, and it was a discussion. But we just need to understand what is the expected course load for the courses.
What's the goal?
Course load. What is the
Oh, I meant to say something that at the beginning. Everyone's going to write a paper.
I see. So
That's all you got to do.
Paper.
And you got to come, and you got to ask questions like you were doing. You got to write a paper at the end, and we'll talk more about the paper. One of the problems that comes up, and a number of the problems have come up already.
A few questions about the paper. Volume and the deadline.
How many, in other words, like more than 200 pages, as you're talking about?
Yeah.
No. Philosophy paper is 12 pages, 14, 15. So people who really get into it, it could be 20 pages, but it's not enormously big. I know that's usually you don't write papers in physics courses, right? No. Yeah, you know how to solve problems. The difference between physics and philosophy is physics solves problems and philosophy makes problems.
It's good difference. I think good physicists should be able to do both problems and solve them.
So, I was interested the way you were asking this business between being a fundamental theory and other theories. When you learn physics, this is what I remember thinking this when I was learning physics, is that you just learn laws, and some laws have, apply to atoms or particles, and some laws apply to fluids.
Yeah.
And you don't really emphasize this distinction between fundamental and non-fundamental.
Any theory has its restrictions. It's area. It's kind of real where it can be applied.
But there's the idea of that there's a theory in principle which applies to everything.
Theory of everything, right? This kind of.
That's the idea. Now maybe that's an idea.
That's a whole.
Yeah, maybe it's an idea that eventually is going to dissipate. But the history of it is interesting. The idea. I don't know who thought of this first, but Descartes seemed to have this idea, and Newton came up with something like a theory which looked like it was a theory of everything. And I think Newton probably thought of it that way, and many people after Newton did think his theory was like that. And people realized that wasn't quite right, so they thought, well, it needs to be adjusted to get another theory of everything. And that wasn't quite right, so that needs to be adjusted. Okay, and maybe adjustings go on forever.
Yeah. I mean, there are certain reasons why physicists are thinking in this idealistic way. Like the 4 fundamental interactions that we know, 3 of them all agree with each other, and there's this one missing. And then we naturally start to ask, how can we just why the 4th one's just lying there by themselves? There must be a way that we can
fit them all together. Yeah. I mean, a lot of progress in physics come about when there are sort of these conflicts or things that don't fit together, and then people figured out some way of fitting them together. I mean, they think of a lot of examples in the history of physics which work just like that.
That reminds me, you were saying something about people. I was thinking when you were saying something about how positions of particles should, in theory, if we take Newtonian mechanics to be the fundamental theory,
right,
that it should actually describe everything in the
right.
Right. But then, isn't there an idea of levels of explanations where a table, its use doesn't come out, it's like an acceptation almost.
It's a what?
Sort of there's a surface and we decided to use it as a table.
Right.
So it's its use something like a use doesn't really come out of is that even a
I'm not even sure. I'm not sure I know what you're saying. The fact that we put plates on it, for example, also follows from the initial conditions
Yeah.
of the world if Newtonian mechanics is true.
So it's like a completely, it's this, it sounds like super deterministic.
Yeah, 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 yeah.
So like a super deterministic theory.
It's not super deterministic,
Just
they're just deterministic.
But
Yeah.
do you believe there should be one deterministic theory which respects everything and
I
everything
don't have any beliefs about what there should be. They're made, you know, if something like Newtonian mechanics were true,
Yeah.
we would have a fully deterministic theory of the world. About